So welcome to Math 246, lecture number 27. We're going to start off the lecture by looking into a short video clip from the movie I Am Legend, starring the famous Will Smith in his heyday in 2007. And you'll find that the clip doesn't show you the mathematics of what we're going to be discussing, but nevertheless, it'll give some context. It has something to do with vampires, humans becoming vampires, and how the vampires conspire amongst themselves to increase their number. In other words, to so-called infect others so that more vampires can be created. So the infected people here refers to the vampires. Let's just watch the clip for a few moments.
I'm not infected. I'm not infected.
Nothing happened the way it was supposed to happen. 6 billion people on Earth when the infection hit. I'm a survivor living in New York City. I will be at the South Street Seaport every day at midday when the sun is highest in the sky.
I hope you're getting the audio there.
Now just sleep. Eat your vegetables. Don't just push them around. Eat them. I'm not playing. More the heck? Midway through the G's. God didn't do this. We did.
Okay, so that was the little clip there that we wanted to show you so that we can set the scene for what we're going to discuss. The clip doesn't explain the details of what was happening in the movie. You got to watch the movie itself to find out how things progressed. What we will do now is a bit more boring. Let's now analyze that the situation using some mathematics. So let's get back to our normal screen. So in this movie, I Am Legend, the infected people, they work together to increase the number of infected. Infected means becoming a vampire here. So we can do a modification of this SIR model that we've been studying so far, tweak it a bit, and then see how it evolves. The tweak that is introduced here is that we replace I by root I. Now, normally the population is normally taken to be 1. In other words, 100%. So if you take root I, actually it's bigger than I. You normally think that the square root of something makes it smaller, but if you're taking a number that's less than 1, root I is bigger than I. Example, if you take the square root of 0, 0, 1. That's 0, 1. It's actually bigger than 0, 01. Okay, so in other words, root I represents an increase in the number of infected. So that's why you see in the model here, you have root I and root I. So just like the disease model, what I shall do here for, let's say, familiarity, we put S to be X and I to be Y. So the model becomes X dot equals to minus alpha X root Y, and Y dot equals to alpha X Y, X root Y, minus beta Y. So that's the model that we have deduced from that. Alpha and the beta are like the infection rate and the so-called recovery rate in the problem, but we need not worry about those at this stage. So let's analyze this model carefully and see now where we can go with it. Now, firstly, let's find the fixed points. The fixed points, I think by now you learned that it's not trivial to find the fixed point, so we should try to do it carefully. You're going to set x dot equal to naught, in which case you can see x root y equals to naught. This means x is naught or y is naught. Okay. On the other hand, if you take y dot equals to naught, this implies that, okay, why don't I pull out a factor of, let's say, y, or root y into alpha x minus beta root y equals to naught. This means that y is naught from the root y, or alpha x equals to beta root y. So you get those two situations there. So now let's call the first one 1, this second set of results call them 2. If we plug 1 in 2, so in other words, put x equal to naught in 2, so you'll get y equals to naught, right? Well, of course, this can give you x equals to beta over alpha root y. Now, on the other hand, if you put y equals to naught in 2, because that's the other option, then you can get x equal to naught, but also you can get, you see, if y is equal to naught, well, you're forced to get x equal to naught from here, you see. If y is naught, you're forced to get x equal to naught. So it turns out that only fixed point is naught naught. Now, this is a bit of a difference from the disease models that we studied recently, where there were an infinite number of fixed points on the x-axis. In this particular case, in this model of the vampires, there's just one fixed point. Okay, so the mystery question now is, what about the stability of this fixed point? If this fixed point is stable, that means all solution trajectories head towards 0, 0. That is good news. It means that the infected and the susceptible drop to 0. That means there's no one susceptible and there's no one infected anymore. In other words, everybody is cured if you reach 0, 0. On the other hand, if 0, 0 is unstable, it means trajectories leave 0, 0, then you have a nightmare scenario where the x and y numbers can increase infinitely, and so the infection will carry on becoming an epidemic, as it were, and then vampires will become infinite numbers. That's the end game here. So the question is it stable or unstable? That's the mystery question here now. Is 0, 0 stable or unstable? So let's analyze that. How do we analyze stability? Well, the tool that we have is the Jacobian matrix. So remember, we've got x dot equals to x root y. That's minus alpha x root y. y dot is alpha x root y minus beta root y, beta y, sorry, beta y. So we need the Jacobian matrix. The Jacobian is day f day x. So day f day x becomes minus alpha root y. And day f day y, that's minus alpha x. Derivative of root y, y to the half, is 1 over 2 root y. So over 2 root y. Minus alpha x over 2 root y. Now day g, day x is alpha root y. And day g, day y is alpha x over 2 root y again, minus beta. Okay, alpha x over 2 root y minus beta. So now let's stick in 0, 0 and see what happens. Right, brace yourself for a surprise. Yeah, so if you put 0, 0 here, the first one will be 0. Now what happens if you put 0 in this entry here? If you insert 0 over here, what happens? 0, 0, that is. So you get an infinite number there. This can give you 0, but again, this guy here is going to be infinite. Okay? So this is actually not good news at all. In fact, you've never seen this before. What the heck is going on here? So this tells us that the linearization stability fails. Linearization stability test fails at 0, 0. Okay, so then what have we got left now in the bag to try? Well, if you can construct the phase portraits, then we might get an idea of where the solution curves are flowing to, right? So let's try to go that route then. So we'll try to construct the phase portraits. So let's try doing the null clines. Null clines, the vertical null clines are when x dot is 0. X dot is 0. That suggests that minus alpha x y to the half is 0. That happens when x is 0 or y is 0. And these point upwards if y dot is positive. What does that mean? Y dot is positive means that y to the half into alpha x minus beta y to the half is more than 0. Right, so now we can break this up into two cases. Case 1, y more than 0. If y is more than 0, it follows that alpha x minus beta y to the half is more than 0. Alpha x is more than beta y to the half. Or you can say beta y to the half is less than alpha x. Okay, beta y to the half is less than alpha x. These are all positive quantities here, so I can square the both sides and I can then get beta squared y less than alpha squared x. Okay, so then now I can say that y is less than alpha squared over beta squared x squared, sorry, x squared. Okay, so now you find that one of the null clines is going to be of a quadratic type, x squared. That's a bit of a strange case. The second option here is to say y less than 0, but this is not acceptable because we're talking about positive quantities here. So y less than 0 is not acceptable. In any case, also we have root y. So you can't have negative there. It doesn't make sense. Right, now let's deal with the second null clines. So secondly, we have to deal with the horizontal null clines. You see, there are some surprises at each step of the game here. Like you've never seen a quadratic type of null cline before, but that's what's going to happen now. Okay, so now you will say for horizontal, y dot is equal to 0. This means that root y into alpha x minus beta root y equals to naught. So y is naught, that's the x-axis, or alpha x equals to beta root y. And that's how you get the same thing, alpha squared over beta squared x squared. So the horizontal null lines lie along a parabola. They point to the right. They point to the right if x dot is positive. That means minus alpha x y to the half is positive. That is alpha x y to the half is negative if you multiply throughout by a minus. Okay, well, you can even multiply, leave out the alpha. So again, we can reduce this to two cases. Let's take x positive. If x positive, then y to the half has to be negative, which is not acceptable. How can you have the square root being negative? Can't work. Secondly, if x is negative, okay, then this is unacceptable because we can't have this being negative. So what's happening here? Both are unacceptable. Okay? So what does this mean then? Well, for pointing right, both are unacceptable. This means that all trajectories point left. Okay, so the surprises keep coming here every step of the game. All right, so now let's see if we can analyze this information and try to give it some meaning in the form of a diagram. Remember, we still don't know about the stability of naught naught. That is the mystery question in the whole puzzle, yeah? We do know that that's the only fixed point though, naught naught, but we don't know whether it's stable or unstable. So let's go back and look at our null lines. The vertical null lines are x equal to 0, y equal to 0, x equal to 0, y equal to 0. The vertical null lines, x equal to 0, y equal to 0. So it is the x and y axes. In these markers here. And then we said that they point up if y is positive or y is less than a certain parabola. This parabola here. Right. Y is positive. So they point up if y is positive, but less than a parabola. So I tell you what, let me put the parabola in because it does feature here. You see the horizontal null lines lie along y equal to naught, the x-axis, and this parabola. Okay, so this parabola, so the horizontals are also there. Let me just put that in. The x-axis is horizontal as well. But then there's this parabola. So I don't know exactly what its shape is, but let me estimate it to be something like that. It's not a straight line like we are used to in the past, but we do know that it is where all the trajectories become horizontal null lines. Trajectories become horizontal on this parabola. Okay, and what we have discovered as well is that they always point left, because you see the calculation above shows us that pointing right was totally unacceptable. So we can then only conclude that the trajectories point this way. And then to finish up, the vertical null lines, the ones that lie below this parabola, are the ones that point up. Okay, like this. The ones above the parabola point down. So now this is giving us a very clear indicator of what kind of a fixed point 0, 0 is. Based upon that, we may now deduce that the fixed point behaves as follows. It is quite reasonable to assume that the fixed point, because things become horizontal there, And then you can see all the arrows going down there. So you can assume clearly that that is the trajectory to be followed in this vampire model. So in fact, all of these behave that way. At some point, they become horizontal on the parabola, and then they go down. At some point, they increase, become horizontal, and then point downwards, following the arrows. These ones very close here do the same thing. They all follow the same trajectory. So I think it's quite convincing that we may now conclude the point. We may now conclude that 0, 0 is a stable equilibrium. We reached that conclusion based upon the trajectories following the null clients. We couldn't tell it by means of the Jacobian matrix test. That failed, but the null clients were a backup strategy, and they gave us the result that we required. So we can now conclude that naught is a stable equilibrium, and now you can pop the champagne there, because it means that the vampires lose and the humans win. So this means that all trajectories, all parts or integral curves eventually tend to 0, 0. Okay, it doesn't matter where you start. You see, if you go up here, and if you, let's say you start somewhere here. Let's say you start off with a point somewhere here. Maybe there's okay, we're using 1 to be the total population. So maybe you could say like 0.5 and 0.3, 50% and 30%. If you start here, it'll follow this trajectory and it'll all tend towards 0, 0. If you start somewhere here, same thing. There will be a curve that goes through that dot, and that curve will follow that trajectory. Right? So you don't have to start on the x-axis anymore. You can start anywhere you want, although the x-axis is also still in the game. Okay? So that's the conclusion we can reach here, that the vampires lose and the humans actually win. That's quite a happy ending. So this is a, let's put it down, a happy ending. Vampires lose. Humans win. Okay, these people are celebrating there on that side. Very good. So but I think one thing you can see from the disease models, even the SIR model and so on, the disease never goes out of hand. It never wipes out all of humanity. According to the mathematical models, even if you tweak them slightly this way or that way, you will find that humanity will never die out. It's not only because of the resilience of humanity, but it's the way the infection works and how people become less prone to get the disease in time. Before I put this away, let me just, I want to actually show you the plot using Mathematica so you can believe that it's correct. But I just want to talk about the basic reproduction number. Basic reproduction number, which is R0, reproduction number, because this is the magic number that the epidemiologists watch to see how the infection is going. The basic reproduction number. So we know that the total number of people is susceptibles plus the infected. Okay? So here we use n equals to 1. Right? That is 100% being the total population. So at the outset, or at the initial position, at the outset, S is equal to N is equal to 1. Now, introduce one infective. In other words, one vampire. Introduce one vampire. There has to be one that starts. So I is equal to 1 over N. In other words, of the population. If you had 10 people in the population, then 1/10 are now infected. So I is 1 over N. The infection rate I dot is equal to alpha S root I minus beta I. And infection grows if the infection rate is positive. If I dot is positive, that is alpha S root I beta I is more than 0. Okay? So here we have, in this problem, we have S equals to 1, I is equal to 1 over N, but we also took N to be 1. So all of these things are 1. Therefore, you can say alpha minus beta is more than 0, alpha more than beta, alpha over beta is more than 1. So we define R naught, the reproduction number, to be alpha over beta. So for example, if alpha is, there was an example, I think, in the tutorial, that's right. If alpha was 0.2 and beta is, say, 0.1, then R naught is 0.2 over 0.1, which is 2. And that's bigger than 1. So infection increases. On the other hand, if you had another example, if let's say alpha is 0.2 and beta is 0.7, then R naught equals to 0.2 over 0.7, which is 2/7, and that's less than 1. Therefore, infection decreases. Infection goes to 0, 0. Decreases and dies off. Okay? So that's how it behaves in terms of those numbers. Now, let me switch to the Mathematica mode. Hang in there, don't go away. It is over, we know the result now, but let's actually confirm the result and confirm the behavior. I want to show you the Mathematica thing because I will change the parameters a bit, and then you can see how things change also. So let me share the screen. Right, so stream plot. Capital S, capital P. Open bracket, open square bracket, open. What is it? Minus alpha xy, minus, let's call it A, minus A times X times Y. And to the power half, sorry. Square root of Y. SQRT of Y. Capital S, you see, this is how the syntax in Mathematica goes. Then you have A times X times square root of Y. A root of Y minus beta minus B times Y. Comma X. Let's take X to be going from 0 up to, what, say 2. And then let's take Y to go from 0 up to 2 as well. Keep it square. Okay, if we simply say draw, we'll get nothing because we haven't said what A and B are. So we got to nominate A to be, let's say, let's just start off with the simple thing of -1. And let's say B is, well, let's take -1 for both. Let's see what happens. Then we can tweak it. Okay, so you get a plot that looks like this. It's actually, in this case, see with -1, 1, the infection increases. From 0, 0, it becomes unstable. Right, so you can see that there is a change in the behavior depending on the alpha and beta. That's what I wanted to demonstrate here. Let's decrease B to be -0.2. Again, you can see it's going outwards. Hang on, have I got this right? Why am I taking, yeah, sorry, there's a mistake. This should be positives because I already got a negative in the problem, right? Let's do this again. So this is what we have been studying. So this is the model we had. So somewhere along here where the mouse is showing, this is where the parabola is. This is where the trajectories become horizontal. It's not a straight line. It lies along some parabola there, but you can see the trajectories following the curve that we have determined. Let me go back and put the 1, 1 there because I had a negative for no reason. Oh yeah, it's fine. It behaves again. Right. Of course, the alpha and beta have to be positive, so then it won't be misbehaved. Same behavior that we expect. Let me now increase the domain and the range. Uh, 5. Now what happened? Did I break it? Let's go to 5. Oh, well, I kept the other one the same, but it's the same trajectory. Nothing changes. I thought you can actually see a bit more. There is a, okay, there's a nuisance object in the way here. That's why I can't see it. Let's change both to 5. All right, you can see it has the same kind of trajectory. What we expected, that is. If we were to change it to, say, 50, see more of it, then you get that kind of a behavior, which is the same. Let me change these numbers here a bit to 0.1 and 0.2 as suggested in the problem. All right, same behavior again. If I change this to 0.7, same type of behavior. It always tends towards 0, 0 in this model, okay, because of the minus and the plus there. Okay, so I think that tells us the true story. Stop the share there. Fine. So that ends that discussion there. That's how it works. So if you have some questions, feel free to ask. Let me just turn off the recording.